All RNA is made by RNA polymerase through the process called transcription, with the exception of the primer that is made by primase in DNA replication. RNA processing or modification changes some of that RNA after it has been transcribed. RNA processing is covalent changes to the RNA, and this involves the forming and breaking of phosphodiester bonds. RNA modification is covalent changes to RNA that don't involve forming and breaking of phosphodiester bonds, but rather are the modification of specific bases. These are most common in ribosomal RNA and tRNA, and not much in messenger RNA. Note also that bacterial messenger RNAs, unlike eukaryotic RNAs, do not have a 5' cap. A number of tRNAs and ribosomal RNA genes are part of polycistronic messages. So for example, we have a 16S, a tRNA, a 23S, and a 5S gene, all on the same transcript. So this is the transcript 5' to 3', and these represent the genes, that is the region that is required for these RNA molecules after they have been processed. Between them are spacer regions that have to be removed. And there's also a 5' end and a 3' end that also has to be removed. This is all done through nuclease processing. So these are RNase molecules that specifically act to degrade the regions upstream, downstream, and in between the RNAs that finally lead to the processed transcript that is 16S, tRNA, 23S, and 5S RNA. 16S, 23S, and 5S are RNAs that are part of the ribosome, and this is one of a number of different tRNA molecules. Post-transcriptional modification occurs most commonly in ribosomal RNA and tRNAs. So this is an example of a tRNA molecule. This shows the secondary structure. The tertiary structure is shown in your book. You should look at that, but for these purposes I want to look mainly at the secondary structure. So one of the things that happens after the synthesis of the RNA is that an enzyme called CCA transferase adds the sequence CCA to the 3' end of the tRNA transcript. So this was the 3' end as it was made. CCA transferase adds CCA onto the 3' end. And this is in what's called the acceptor arm of the tRNA. In addition, some bases are covalently modified. So in the region called the D loop, which is over here, uracil is modified to dihydrouracil. In this loop right here, we have pseudouracil that is put in some of the bases in this loop, and uracil is converted to thymine. You recall that thymine is not normally present in RNA, but in this case we have a T in the RNA because it was modified from uracil to thymine. And in the anticodon loop, usually right in this position, there is often a modified purine. So these modifications occur post-transcriptionally and are most common in tRNA and ribosomal RNA. RNAs typically don't last a long time. This is particularly true of messenger RNA, which has a very short half-life. That means that once the molecule is made, it is fairly rapidly degraded, in some cases within 2 or 3 minutes, and this is in E. coli, which has a generation time of 20 to 30 minutes. The RNA degradation pathways include nucleases that are endoribonuclease that cleaves within a sequence, and also has 3' to 5' exoribonucleases that chew away from the 3' end. A stem loop structure at the 3' end of an RNA molecule makes it resistant to the 3' to 5' exoribonucleases. It's protected by the secondary structure. So this molecule is still susceptible to further endoribonuclease activity and is still susceptible to a 5' to 3' exoribonuclease, shown here. Also, a few RNAs in bacteria are polyadenylated, and these are rapidly degraded by 3' to 5' exoribonucleases. Polyadenylated RNA is not common in prokaryotes as it is in eukaryotes. However, there are some molecules of RNA that are adenylated, and these are susceptible to degradation. So every time there is an endoribonuclease, then the 3' end gets rapidly degraded. So by a process of endoribonuclease and then primarily 3' to 5' exoribonuclease, the molecules are degraded down to very small molecules, with only a few exceptions, and that is molecules that have stem loop structures which are resistant. So the half-life of a messenger RNA molecule is controlled first by its length, but also by secondary structure, which protects it from degradation by the most common exoribonucleases, which is the 3' to 5'.